Okay, so we started with computer vision yesterday. Computer vision, the object detection is the first one to do in computer vision. And in computer vision, there are many applications. If you take a robot trying to put something in a shelf, or a robot trying to pick up something, right? There are two components there. One is major components basically. One is mechanical, and second is intelligent, the brain kind of stuff. So mechanical thing is moving the hand, but how far it should be moved and where exactly the object is a computer vision thing. So when you have a camera to the robo, that camera should actually understand the uh, distance at which the object is present in which direction, and in how much distance the object is present. Then only the hand can move accordingly and pick it up. Right? In a controlled environment, doing it is very easy, but in a open space, right, where you don't know the measurements, doing it is difficult. Okay, so computer vision, right? So in that case, right, the robots will take help from sensors, and it reads some data along with the camera input. Okay, so object detection is the first component, and then object tracking is the second thing. With both, right, with both and the 3D to 2D calibration, we will be able to do whatever I said. The robot trying to pick up something. Okay? We are not going to do that now. Maybe in future we'll definitely want to do that, right? But for now, right, we'll try to explain what is object detection. Object detection has got two components in there: classification and localization. First, it need to identify what object is present in this image. Is that a car or a bike or a human being? It should identify, and then it should actually localize it. It need to do a bounding box around it. We call this as bounding box. And this is object detection. We can do this with normal machine learning or deep learning algorithms. The way we should be doing it is take closely cropped images of dogs. Right? Cropping, right? So you take many dog images, closely crop only the dog image, right? And then train a classification model. And then you take this picture and cut it into pieces like this. Right? You take first piece, second piece, third piece, fourth piece, like that, and then you pass that to the model, right, like this, and the model will predict it. Whether the picture, the part of the picture has got dog or not. When it finds the part of the picture, right, you can do a bounding box around it. But here you will find many places where dog is present. Maybe it may not be identifying this one and this one as dog, but these two it may identify. So in this whole process of sliding window, you may identify many dog images, but you need to find out the exact place where it is found. Right? That is, we have seen Jaccard coefficient, right? We use that technique here, intersection over union, to identify exactly where the picture is present, right? Object is present. So this is one way. The other way, right, you need to use CNN. So if you use DNN, you have to cut the image into multiple pieces and pass it. But in a CNN, it is already doing the uh, sliding window classification, right? The filter will actually slide through the image and then try to do classification task, right? So doing object detection task using CNN is easy because it actually does the sliding window classification. Okay, so the next point is, this far it is good, right? Any questions? The next part, and a little complex part, yesterday I tried to explain, was a CNN neural network that has fully connected layers at the end, and a CNN network with no fully connected layers, all CNN layers. You see this network, it is all CNN layers. The advantage of using all CNN layers over the CNN network with fully connected as the fully connected as the last layers. Okay. If I have to explain this in a single point, yesterday I took 1.5 hours of class, but if I have to explain that in a nutshell, right? If you have these fully connected layers, when you want to use the same weights, you actually craft the image and you train the network, and you want to use this this same network or same weights, not network, same weights on a bigger image, you will not be able to do it, because by the time the network, the weights, right, these filters reach here, the dimensionality will change. We are getting 5 by 5 by 16, right? If you pass 28 by 28 by 3, by the time it comes here, it will be around 9 by 9 by 16 or something, right? So some dimensionality, right? So that way, right, this fully connected layer cannot take that input, because fully connected layer expects always the same size. But in a CNN, right, you can actually do that. Even when the image is big, you can actually take these weights and do a prediction on a bigger image. How can you do that? Like this. So this is a 28 by 28 by 3 image, and when we actually try to use this 5 by 5 by 16 filter, right? 5 by 5 by 3 filter, sorry, 5 by 5 by 3 filter, you will actually get a 8 by 8 number of blocks there. Did you get it? No. A 5 by 5 filter will find 8 by 8 blocks in this 28 by 28 by 3 image. 28 by 28 image. Got it? Got it? Yes, no?
No, sir.
No. Yesterday's video did not watch?
No, sir. I couldn't understand. I watched half of the video.
You couldn't understand. Should I explain it again?
Not yesterday's, but whatever we are going, continuing, we can.
No. Yesterday's video, if you did not watch and you want to watch it today, that's fine. Right? If you already watched
Yeah,
and
yeah.
you did not understand anything, I'll just try to I'll just recap it. Maybe for maybe 15-20 minutes. Should I?
Yeah, I think. Yes.
Yeah. Okay. So I made a statement that let me take a screenshot and then start explaining this. This is the very basic thing, very fundamental thing for object detection, and I have created a OCR model. I have created a simple OCR model, not a perfectly tuned OCR model, but the basis for OCR model, and we followed the same in number plate recognition in our speed detection system. Okay, so this is all kind of research work, and I am taking a lot of time in kind of creating the code components there. But by now we had this. By last batch we had this, but I was thinking of doing it for long time. We have many things to do like these. So let me take a screenshot. So this is a neural network. Okay, this is a neural network. Here, these are fully connected layers, right? Right. These are not the last one, but these two are fully connected, right?
Yes. Yes.
So here, right, in the theory, what I said was, I said that if it is a DNN network or a CNN with DNN network, you need to crop the image and pass it to the network. Rather, the network will not work. Okay, that is one point. The second point I said is, if you have a CNN network, you can actually slide through. Okay, that's the second point, right? If you look at this is a CNN network. but there are DNN layers there. Okay, this is a CNN network with all CNN layers. Do you understand the difference between these two as network at a
Yes, yes,
high
sir.
level?
Yes.
Right. So when I said this and this statement, right, I am actually trying to prove that how a completely, fully convolutional neural network can be applied onto a bigger image, and a small, and a neural network with fully connected layers cannot be applied on a bigger image without cropping it, right? You have to crop it. If you have a DNN layer in the network, or if it is completely a DNN layer. What is this DNN layer? A DNN layer trained on closely cropped images. What is the closely cropped images? Suppose that this is a classification, multi-class classification problem where you are trying to identify a dog, a cat, a horse, and an elephant. You are taking, maybe 1,000 pictures of dog, maybe 500 pictures of cat, maybe 200 pictures of horse, and maybe 300 pictures of elephant. Closely cropped. There may be a big picture, but somewhere here there is elephant, somewhere here horse. You cut it, you pass it to this network, and you train it. Okay, that's the first thing. Okay. Now, now this network is trained and it is able to identify, it is able to classify a closely cropped elephant or horse or a cat or a dog. That far you are clear? This is a network which will classify a closely cropped dog, cat or horse or elephant. That part is clear?
Yes, sir.
Now I am taking a bigger picture, right? I am taking a big picture where I have a cat here, I have a dog here, right? I have a horse here. Right? Now I want to classify. Right? I want to send this picture to this network, or right? I don't want to send this image to this network, but these weights are trained, right? These weights are trained. Do you agree? These weights are trained. Do you agree?
Yeah, yeah.
I want to use these weights to make prediction. To do that, what I need to do? This is a CNN, right? This is a CNN. I can actually slide through, right? Right?
Yeah.
But what I said was, because of this DNN layer, you cannot slide through. Okay?
Yeah.
Why that is? I am going to explain. Suppose that this is a 28 by 28 image. Okay? 28 by 28 by, I don't care how many channels. Okay? So if I take these weights and try to do the next CNN, what happens? 28 by 28 by 3, how much size it gets? If I apply these weights, 28 minus
28 minus
plus 1.
plus 1.
Yeah, n minus f plus 1. There is no p, right? So this is
24. Yeah.
So this is 24, right? So you get it 24 by 16, because 16 filters are there, right? Now I am using these weights, right? Because these weights are already trained. They know what is a dog, what is a cat in this place. So so in every slide, basically it actually takes the cut, sees whether it is a dog or cat or horse or elephant. Again it takes that cut, sees that whether it is dog, cat, or whatever, sees that, takes that cut, like that it actually slide through. That is sliding window classification, we call it. You can actually manually do it by cutting the image into slices, or software wise, you cut it and pass it, or you use a CNN layer that actually does it. But when you have DNN layers in between, it is going to cause problem. How is it going to cause problem? Now there is a pooling layer with filter size 2 and the the stride 2, right? It is going to be 24, right, plus 2p. P is not there, p is 0, because for pooling layer there is no pooling, right? You can add pooling also, right? And then here there is no pooling, right? Minus 2 divided by 2 plus 1. S, right? Divided by S.
Yeah.
N minus F divided by S plus 1. So 22 by 2 is 11 plus 1 is 12 by 12 by 16. Right? That's the out. Now here we have 5 by 5 by 16 where 400 inputs are going into this 400 nodes. Right? But here 12 by 12 by 16 we got. That's a that's a different dimension. Right? 12 into 12. We have got 2,304 inputs, but the network is expecting only 400 inputs, right? Can you take a deep neural network and pass a bigger bigger input?
No, sir. It should be the same.
Same dimension. In linear regression, logistic regression, these are all like if you take this as a logistic regression, when you trained, it has got 400 weights, equation with 400 parameters, right?
Yeah.
Equation with 400 parameters. Now you want to send 2034 parameters, it will not work, right?
Yeah.
Right, that's the problem. So if you take a DNN, complete CNN layer, fully convolutional neural network for all object detection models, this is the basis, right? What we are understanding is the fundamental, okay, basic fundamental of the whole thing. Okay, so I have taken screenshot of this, and now, right, if you have a network with all CNN layers, what happens? The same scenario. Again, what I did, I took a neural network with all CNN layers. I took a dog, cat, closely cropped, horse, and elephant. Okay, images closely cropped. Again, 1,000, 500, 200, 300 images. I trained this model. Okay. Now I am going to take a bigger picture, right? Big picture. And then there is a dog here, there is a cat here, maybe dog here, cat here, and horse here. Now I wanted to, this is already trained. Maybe 1,000 iterations I trained, right? These weights are actually able to identify the dog, cat, and horse and elephant appropriately and a closely cropped image, right? Now I wanted to use these weights, right? These weights to make a prediction on a bigger picture. But the point here, one point we need to understand here is, if you look at this, right? So till here, right? This 14 by 14 by 3, you applied 5 by 5 by 3 filter. 14 minus 5 plus 1 is 9 plus 1, 10, right? And you are applying a pooling layer. This is 2. I need to correct this in the image. This is 2. Right? When you apply that 2, right, it's going to be 10 minus 2 by 2 plus 1, right? 8 by 2 is 4 plus 1 is 5 by 5 by 5 by 16. If you see carefully here, the filter size is also 5 by 5. What is the filter size here? 5 by 5 by 16, right? So if you do convolution of a 5 by 5 by 15 matrix with 5 by 5 by 16, what will happen? Will you get a matrix or a single number? Yesterday also I asked the same question. I have a 2 by 2 matrix, right? 2, 4, 3, 2, 3, 5, 1, 2.
1.
Now you will get one number. When you do convolution, what you do, it's a linear combination, right? What is linear combination? 2 into 1 plus 4 into 2 plus 3 into 3 plus 5 into 5. This is all going to become one number. So when the convolution, the filter size and the input size are same, input dimensionality are same, you get 1. So I am actually for one if you apply one filter, you will get one number. Second filter another number, third filter another number, fourth filter like that 400 filters I am applying. So you will get a 1 by 400 dimensional vector matrix. Got it?
Yeah, even if we apply the formula also, it will be same, right, sir? N minus F plus 1.
Definitely formula is same, but logically if you try to see, right, this point very, very important, because it doesn't matter what is the dimensionality of your input. When you take the filter size same, it gives you one number.
Yeah.
Yeah, that's, when you apply the formula also same thing happens. Same thing should happen, right? So again I took filter size 1 by 1 by 400 it is. 1 by 1 by 400 dimensional filter. And now I apply, I get, for each filter application, I'll get one number, right? Now I have taken 1 by 1 by, these are called as bottleneck layer, right? 1 by 1 by whatever layer is called as bottleneck layer. We'll understand that, okay, in coming class. But 1 by 1 by 400, right? I took only 4 filters because I have 4 classes: dog, cat, horse, and elephant. Got it? On a DNN, on a CNN DNN layer, the last layer is actually having 4 nodes, right? For 4 classes, 4 nodes, right? Here also, we have simulated the same scenario here, right? You take, appropriate maybe sigmoid function, right? Sigmoid function you take, it's going to give you wherever the, whichever the class the record belongs to, it will give highest probability there, right? You take argmax, you know which class the record belongs to. Got it? Got it? Did you get it or not? When you apply the filter, you will specify the activation function. Instead of ReLU, if you say logistic regression, you get 4 numbers, 4 probabilities, and you try to pass it to the, one hot encoded target variable, where it will try to adjust the weights, and ultimately it will find out the appropriate predictions. Got it?
Yeah, yes, sir.
Any clarity needed? Anybody? Okay. So we have implemented this. I implemented this whole code, right? I'll show you the example. Okay. I implemented OCR, optical character recognition base model, very base model. Okay. So if you take a 28 by 28 by 3 image and you use these weights, right? When I am saying I am using this network, I am not actually, passing the input to the same network. If I pass this input to the same network, right, it will throw error because the input dimensionality is 14 by 14 by 3. So what I need to do is I need to design a new network, right? That will actually be like this. Right? I need to design a new network that will be like this. I'll show you that actual diagram. I'll show you. That will be using these weights. I am not going to train it. I am going to copy these weights here. Copy these weights here. I'll show you how to copy the weights here. Copy the weights here. Copy the weights here. Right? Then what happens? This network is like this network only. Do you agree? If I copy the weights here into create a new network with input size 28 by 28 by 3 and copy these weights, this is like this network only, right? Train network, right? Do you agree? Yes, no?
But will the dimensionality is different, right? With
Yes,
that?
yes, I'll talk about that.
Okay.
That's the point. And dimensionality changes, but it will not throw error. And we get a more advantageous outcome. I'll show you in a moment. Okay. So when you do that, the point is that you copy the weights. It works like the previous network. It is like intelligent one now. Okay. Now what happens when you apply 28 by 28 by 3? This is going to be 24 by 24 by 16. Then you do this whatever the pooling layer. Right? Pooling layer 24 minus 11 plus 1, 12 by 16. Now you do 5 by 5 by 5 by 5 by 16 filter. The size dimensionality did not change here. 5 by 5 by 16 filter. You applied. What happens? 12 minus 5 is what? 7 plus 1, 8. Right? 8 by 8 by 8 by 8 by 400. Right? Right? Now you apply again 1 by 1 by 400. 1 by 1 by 400. What will happen? 8 minus 1 by 8 minus 1 plus 1 is 8 only. 8 by 8 by 400. Right? We are getting big number. And now you apply 1 by 1 by 400. What will happen? 8 by 8 by 4 you get. Right? 8 by 8 by 4 you get. What is this 8 by 8 by 4? I have the diagram, I think I can show that. What is this 8 by 8 by 4 is this one. When you apply, right, that same weights, right, like this it actually reduced, and this 8 by 8 by 4 is this diagram. In this 28 by 28 by 3 picture, there are 8 blocks, 8 by 8, 64 blocks of 14 by 14 images. In this 28 by 28 by 28 by 28 image, there are 64 blocks of 14 by 14 croppings. Got it? Sliding windows. If sliding window slides, this 14 by 14 slides, sorry, this 5 by 5 by 3, 5 by 5 by 3 is the sliding window, right? So this 5 by 5 by 3 slides through this 28 by 28 by 3, it would have done the convolution 64 times. Are you getting it? Are you getting it?
It's just trying to visualize.
Yeah, just visualize, this, there is a 14 by, 5 by 5 filter applied here, 5 by 5 filter applied here, 5 by 5 filter applied here. If you apply like that, right, there will be 8 blocks here, 8 slidings it will happen through this direction, 8 this direction, right? That way it is 64. It will happen 64, convolutions. Okay. It may, this 8 by 8 is that actually.
Okay.
It is actually trying to find 64 areas where it may find a dog or a cat or a horse or a elephant, right? So, the first block belongs to dog, second block belongs to cat, third block belongs to horse, and fourth block belongs to elephant. If you have one here, right, in this particular cell, that means there is a dog here, in that area. If you have one here in this area, right, that means there is a cat in that area, right? If you have one here, that means in that block there is a horse. If you have one here, there is an elephant. In a single picture, if you have 4 objects, you can find them. Each of these, channel will give you the, the exact object present. You take argmax in the depth direction, you get, give me 1 second, I'll be back. If you take argmax in the depth direction, right, you get the class for, in that particular area, which object is present. Got it?
So here 8 by 8 is a matrix, that's right.
Ah,
There are 4 layers with 8 by 8 matrix.
yeah. See, I'll show you this diagram once. Right, if you have 14 by 14 by 3, the way we design network is that you get only 4 classes, right here. This part you understood? Is this part clear?
Yes, sir.
4 classes, right? If your picture is big, right, what will happen? These kinds of blocks will increase, right? If you use the same weights, right, blocks will increase. The blocks will increase. There, it actually found 8 by 8, 64 blocks of this kind. Each block is a particular area in the picture. Each block, each 1 by 1 by 4 block is particular area, 5 by 5 by 16 area, 5 by 5 by 3 area. Is there an object present in that area? What is the object? If you have one here, that is dog. If you have one here, that is cat. If you have one here, you have one here, that is elephant. we'll get only one. It's a multi-class classification. Only one.
Yes, sir. Yes, please go ahead.
Got it?
Yeah.
No. This is the key, right? This is the key. You have this kind of you think that this is a brick, right? You have here 8 bricks.
Yeah.
Sorry, 8 by 8 bricks. Each brick is a 5 by 5 area of the picture. Okay. 5 by 5. 14 by 14 by 3, right? Actually, this 5 by 5 filter is actually taking 14 by 14 by 3, right? So 14 by 14 area. Sorry, this is each brick is a 14 by 14 area. It actually takes 14 by 14 area and tries to predict whether there is an object present or not and which object it is. Okay. So let me show you the code. Maybe you'll get better idea. Is it okay if I take class till 9:30? So yesterday I already explained, but this is the one. So fully convolutional neural layer and neural network I have taken and implemented the OCR. Wow. Yeah, this is the one, right? What? Yesterday I showed you that, right? What happened? Did I do something? Fully connected. Yeah, this is the file. Okay. So suppose that there is a sheet with handwritten digits. Okay, there is a sheet, handwritten digits. You need to identify, by reading this picture, you need to identify the handwritten digit. Okay, that's the OCR, right? This is an image, and we are going to, run the CNN model, right? The CNN model will actually do that slide, that slide, that slide, that like that. It will slide and then find out whether there is 5 or 2 or whatever is present or not. Okay. So the problem statement you understood, right? Understood, right? Can I move on? So what I did, I just took this normal thing, right? Normal data. Give me 1 second. Okay. Data, and then I converted this target variable into one hot representation, because if you look at this, when you are doing a fully convolutional layer, the target variable will get 4 values. For 4 classes, 4 values will come. Here in this example, right, 10 classes, 10 values will come. So your target variable should also have 10 values. That's where I converted the target variable into one hot representation. And then I built a fully convolutional neural network. See this here? There is no dense layer. All are convolutional. See this? Right? So 3, 6, 12, like whatever, right? And then even target variable is target layer is also a convolutional layer, fully convolutional layer. So that this is how it is, and there are many parameters, right? There are around 6 lakh parameters. Okay. Now I train the model on the closely cropped images of handwritten digits. I train the model. Closely cropped images of handwritten digits. I train the model. Okay. And then, right, I am actually trying to take this 112 by 112 by 1 image. What is that image? This one. Bigger image. I trained the model on a 28 by 28 by 1. See this? I trained the model on 28 by 28 by 1 image. And I need to make prediction. I need to do OCR on 112 by 112 by, this is 112 by 112 by 1 picture it is. Okay. On this I need to do the OCR. To do that, what I did, see this here. I have taken this neural network, right? I built a neural network again. Okay. With the input shape as 112 by 112 by 1. The remaining network whole structure is same. The architecture here and the architecture here are same, but only input changed. Okay. Now what I will do is I will copy the weights from the 28 by 28 by 1 image that model into this new model. See this here. The OCR model is the big model, 112 by 112 by 1 model. HR model is the base model. This is 28 by 28 by 1 model. I am copying all the variables into this. That way, right, all weights will come into this network. It is like trained network now. Okay. Now when I do sliding window, right, now I do sliding window on this picture, it is actually finding 85 by 85 by 10. Right? 85 by 85 numbers it found, right? With each class, right? 10 classes you will get 10 probabilities for each of this 85 by 85. So I actually kind of did argmax on axis 3, the 10th dimension. I got these, see this here. This is how it is. That 85 by 85 predictions are all like, it predicted 5 around 10 times because it was sliding like here. Again slide a little bit, slided a little bit, slided a little bit, slided a little bit, right? Because the first this filter size is too small. That's where the network is actually taking too many, right? Too many outcomes. Right? If you increase that, right? So maybe let us do that experiment. Let me comment. Let me take this one. Guy, did you get the concept? Any questions?
Yeah, one question, sir. So, by manually looking at the picture, what are the cropping size we need to do? If we have a better idea on that, then it will be more accurate. Is it a correct statement, sir?
No. Whatever dimensionality you pass, no, this you need to shrink the image to the model's input. No? There are three things, sir. One is closely cropped image, whatever dimensionality is there, you don't care. Right? You take some dimensionality, right? You train the model, and then you see the you try to find out the in real time in production what is the picture size you are getting, the dimensionality. For that dimensionality, you make that input layer, and then take the same network, and then do the prediction. So once you did that, right, that's like I think I made the point. I don't. I'm. Oh, see this here. I have okay. I think I have to take this out. Oh. Did I answer your question or I got confused?
No, it's not clear, sir. Because the reason I asked that question was, anyway, if you are doing something, you please move on. Maybe after this we'll discuss.
Yeah. Let me execute this and
Yeah, sure.
Right. While that is executing, we'll talk. why did I took this only digit recognizer? Because of this, I wanted to show how OCR works and these kinds of exciting stuff. But I think the API changed. These guys, Okay, okay. Okay. This dimensionality is very small, right? So, maybe I should take 12 by 12. Okay, this is actually shrinking. So now when you apply 24 by 24 by 1 on this, right? What happens? It becomes 2 by 2 by 3 by 3 by 1, right? So there is no, yeah, we cannot do that. Let me. We cannot do that, because the network is shrinking a lot, and if the image, if the original image is big, then we were able to do that. Logits and labels must be broadcastable. Something went wrong somewhere. This was working. Logits and labels must be. So logits here are output layer are the logits. Did you get the error statement here? What is it saying? Logit size, right? 2407 by 10, right? Label size is 16 by 10, right? The input um, uh, label size 16 by 10. So this one should also be. Do you know what is logits and why that is coming? Two 2704. Why 2704? Let me try to restart kernel. Yeah, now it actually previous whatever the error was there. Yeah, go ahead, sir. What is the question? Giriga.
Yeah, can you please go to that picture, sir, digits picture?
It will not be appearing now. It will take time.
Okay,
Yeah.
no problem, sir, no problem. In that picture, we have the digits. So assume that with the close cropping for the given size of the digit which is present there. Let's say already training was already done on the with the close cropping. Okay. Now on the big picture, the size of the digits, let's say, is different. Let's say it's big. Assume it's big compared to the size on which it was trained. So my question was, when we are trying to do that sliding or the cropping on the big picture, the way we need to choose the parameters is such that it fits, or at least close to it fits the digit size. Is my question. I just want to confirm.
Yes, sir. If it is a printed document and if you have different font sizes of the letters, what should we do? That's the question, right?
Yeah, correct, sir. Correct, sir.
We need to train multiple models on different fonts and different font sizes. We need to build, train multiple models, and then for the input size image, you need to copy the weights of all those models. If you have 10 different weights, 10 different sized letters, you need to build 10 different fully convolutional neural networks. And for your input, image dimensionality, you need to build the network and copy those 10 different models weights, and you will get 10 models again here. Now you need to pass your picture into all 10 different classes, and then you need to take the predictions into consideration, and then only it will work.
Okay, sir.
That's a very good question, sir. Actually, the OCR guys, no, I said this is just a base model because of that reason. I am not doing all the fine tuning and all that activity. I just created it. I just created to show the example or how exactly the CNN is working. I wanted to show. This should give you a complete picture of the object detection. Okay, at a level it should give complete. Any questions here? Let it run. I anyway uploaded this yesterday. Good, right? Can I move on? Okay. So here, right, the first thing, right, what we had was object detection, right? So in our digit recognizer, right, to train our model, how was the data structure? How was the input and how was the output for our digit recognizer? How was the input and how was the output?
Input was 284 by 284.
784 pixels.
Yeah,
And
784.
output is labels, right?
Labels.
Because of that, we were able to train a classification model. To train, object detection model, right? We need to do classification. So we need to have, for each picture, right? We should have the class, the y variable class, and then the dimensionalities also we should have. So the y variable will be like this. Okay, whether the object is any object is present or not. If it is present, the bounding box dimensionalities, right? What is the width of it? What is the height of it? Right? Where is the origin? Right? Origin of bx by is the origin. Where is the origin of the picture? Right? So, and then which class it is? Okay, if you are trying to see car, bike, and a pedestrian, right? Which class it is? 0 or 1. Okay. So in some pictures, right, you may have both, but we'll see that later. Right? At a high level, right, the target variable of the data should be like this. Okay, so this is what is called as labeling the data. Right, to do our speed detection system, the team has actually done labeling of around maybe 4,000, 5,000 images. Now they are actually working on around 16,000 images now. So that labeling task is very important. Right? There is manual work involved in creating the data set to make the object detection work perfect. Got it? Got it? We have to create these labels. This is a y variable. This is basically this y variable for one image, where it says object is present or not. If it is present, wait, what is the origin? What is the width and height? Where exactly which object it is? Either car, bike or pedestrian, like that. Okay. So if you have this kind of data, right, you can go ahead.
So let's say this is an image with some dimension, right? So it is converted into number format, right? And let's say if we are manually labeling it, whatever the researcher or the analyst, someone will open it and mark it. It's a car. So, but then that will be 1. The class will be 1. But how the labeling happen? Like what is it, this 0.5 or how
So this
this
is
will
one
be
example.
measured?
this is one example, right? This is one example, but we have tool called as IMG label. I'll show you, but image labeling tool also I'll show today. So this is the tool, right? You know, this is how you actually do. So you open this tool and then open your picture and then do a bounding box around it and specify the class. That way it will actually create a XML file. Example was not good. So let me download an image. I'll show you how the labeling is done. Okay, let me download this. I think I can directly install. I can do it. Let me do that pip install in here. So I wanted to show you how exactly the labeling is happening. In theory, right, we showed some y variable, but exactly that's not going to happen, right? Depending on the way we the approach we take, right, it will change. So it may change. Okay, so it is successful. Now to open that, what I need to do is the Jupyter notebook is in um, T-flow, right? T-flow. Yeah, T-flow.
T-flow virtual environment.
Yeah. So I created torch yesterday. I don't know. I would have on the activate T-flow. Now we should say the labeling. What happened? Let us see. It's not working, right? I'll download it and show. See, it opened up. Okay. Right. Now I open the image. We'll download. Right. Now I do cropping. How do you do it? There are two ways of doing it, Pascal and your way. Right, I actually click W and now it does that. Right, and they need to specify the class car. Okay, now I save it. Right, that gets saved as XML file. Right, let me go into the folder and show you how exactly. This is the XML file it created. Open with I think. Okay. So here, see this, the folder in which the car is present, the name of the file, and the path, right, and then the width, height, depth, right, car, right, truncated, whatever the xmin, xmax, right, xmin and xmax, right, xmin, ymin is these two coordinates, right, xmin and ymin are these two coordinates. Xmax and ymax are these two coordinates. Right? In this particular tool, the XML file is creating. Where is it? This kind of a labeling. So in this label, right, what we have? Object, the class name is there, right, for classification. And then to detect object, right, we have these bounding box. Okay, and width and height. So these are it's actually the pixels, right? This is 640 by 450 by 3 is the dimension of the picture. This is the classification, whatever data is needed. But in theory, right, I was actually trying to show you some example here. Maybe origin, maybe width and height, and then classes what. But here in real time, we are going to use this kind of a structure for object detection. You have to use this tool. You have to use this tool. I will show you a resource where you actually can do the object detection today. Right? You should be practicing it from tomorrow. Right? You should be using this tool. And label IMG. Remember it or write it down. Okay. These kinds of XML files will pass, and then there is a small program that actually converts this into a data set, and then we'll use that data and train the model to do object detection. This is called as bounding box. Manually, we are doing bounding boxes like these. Got it? Did I answer your question, Seshirangar?
Yes, sir. So actually, who will do this labeling? Is it
Generally,
the data?
junior case, juniors who are actually learning will do it. In our team, right, we have 4 people who are kind of learning now. So we are using, their time to do this labeling stuff. And we have 3 guys who are actually a little more, proficient. They are actually doing the training. I never got involved into that speed detection thing. Pawan was the one who actually did both. So team is able to do that. Then junior guys will.
Okay, got it.
So you shouldn't be spending 30 lakhs to do this labeling stuff, right? So
yeah,
maybe 3-4 lakhs package is fine, because whether that guy does a web application or this one, the amount the budget we spend there is going to be reasonable. So that's the first task to do. When you actually want to do object detection, this is the first task you should be doing. And we'll understand YOLO algorithm at a high level. Don't get stuck with YOLO algorithm, because I am showing you YOLO 3. Now there is YOLO 5, and everything we may not be able to understand, but the model works and the basics we know. Okay, so let me show you that. So in YOLO, what it does is it actually takes the image and splits that image into a grid. What is this grid? Here, when I did OCR, right? When I did OCR here, I have got 85 by 85 grid, right? Right? When I did OCR, what happened? Where is that? Not this one. Where is that? I closed it or what? Yeah, here. Still running. Okay. So here I got 85 by 85 grid, right? Like that, YOLO will actually try to split this into some kind of grid, and then it does it actually tries to find out. It's not 85 thing. Sorry, it is not 85 by 85 thing. It will try to divide the image into a 9 by 9 grid, or some kind of grid there, and it will try to see whether the object found in that particular grid. It will try to show that the object, No, there may be many times the object is found, right? When you are actually sliding, it may be found there, 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 right? In this down below also it may be found, but the origin of the picture's origin is there, right? If that origin falls into this area, right, we will do bounding box there only. In whichever grid cell the origin of the picture falls into, we will do a bounding box there only. Okay. So this is bounding box, this is class, and whether the object is present or not. Right? In YOLO algorithm, YOLO 3, they took like this. But in other algorithms, right, it is not like that. It maybe it is like this. You know, this Excel sheet kind of a thing. Okay? Min X, min Y kind of structure they have taken. So don't get stuck with one algorithm because there are many algorithms. Okay. So there is one concept we need to understand. In YOLO, or any other algorithm, intersection over union. This is Jaccard coefficient concept. So there is ground truth bounding box. What is ground truth bounding box? You take a picture of road, right? I'll actually show you. Maybe next Saturday when we have class, right? I'll show you how we did it on our project. Okay, I'll show that. So what you do is you take a picture. There are many cars and bikes in there. You do bounding boxes manually around those, around those objects like this. To the dog we did this bounding box, right? Like that for all the objects we do bounding boxes. Okay, so that is called as ground truth bounding box. This red one is ground truth bounding box. Algorithm while sliding, right, it will actually find a bounding box. If this algorithm's bounding box is overlapping on the red, that's the correct one, right? Right? Do you agree with the statement? This violet color bounding box, if it is overlapping the red color bounding box, that's the correct one, right? That's the correct identification of the object, right?
Yes.
Right? When I'm saying that, right, what is happening is intersection between this violet color and red color is equal to union. When they are overlapping on each other, right? So you try to do, the sliding window. Always you try to find intersection over union. Whichever intersection over union is high, you take that as the bounding box for the object detection. So in our OCR model, right, I did not do that. I did not do intersection over union. That's where it is actually giving me, all those fives, n number of fives I am getting, right? If I implement intersection over union here, and I take the maximum intersection over union bounding box and the object, I would have got only, whatever, number of letters there, that many I would have got. Got it? Got it? In object detection, intersection over union is very important. You may find the object in many sliding windows. To choose the appropriate sliding window, intersection over union is useful. The maximum intersection over union is the sliding window. Okay, there will be threshold also. If there is a threshold, right, 0.6 you kept, you will consider only the bounding boxes which are, there will be bounding boxes and there will be bounding boxes which will be finding dog, but the intersection over union for some will be more than 0.6. The less than 0.6 you will not consider. And out of the more than 0.6 you take the maximum. That to reduce the number of calculations. Got it? Choosing the bounding boxes whose intersection over union is more than 0.6 or 0.7 or 0.8 is called as non-max suppression. Okay, IOU and non-max suppression are the concepts used in most of the object detection algorithms. Did you get it? Non-max suppression and IOU. This terminology is used when you are actually reading through the articles and the papers, right? This terminology is used throughout. Did you get it? Any questions there? Non-max suppression. Okay. Non-max suppression, two ways you can think of it as, only take the bounding box which has got maximum IOU, right? And considering only those bounding boxes which are greater than the threshold is the next thing. No, you try to find a bounding box, and you are sliding, and the model found that the object is present, and immediately you calculate IOU. Is that greater than 0.6? If yes, you take it and put it aside. If no, you will not, you will leave it and move forward. Again do bounding box. Again do sliding window, bounding box, and see whether it is greater than or not. If it is greater than, keep it. Take that into consideration. Do one more slide, see whether it is greater than 0.6, and see whether it is more than the previous ones, IOU. If it is more, right, you will suppress the old one, take the current one. Like that, the algorithm will actually slide through and find out exact place where the object is present. Got it? Got it? Non-max suppression and IOU. Along with these two concepts, right, it will actually consider this grid also. If the labeling tool is actually taking the origin also into consideration, right? This is not taking the origin into consideration. If the labeling tool is taking origin into consideration, and if the implementation has got this kind of an setup, right, then it will see in which grid cell the image's origin is falling along with IOU and non-max suppression. It will try to see in which grid cell the origin is falling. It will try to take that particular bounding box as the final bounding box. When you are doing sliding window, you will find, the algorithm will find many bounding boxes. Okay, out of those bounding boxes, you need to finalize one. That problem we have seen in my OCR model. I have got 85 by 85 different findings, but some are right, some are wrong because of not considering IOU. I did not implement it. When I get time, I'll try to do that. Right. So if you are able to do these kinds of things, right, you can actually tweak the existing algorithms and make the models work. Why am I saying this is, for speed detection, Pawan actually tweaked the deep sort algorithm, and he was the one. It's a kind of research work he did to deliver the product. So in some cases, you should be able to deliver the product like that. If you are planning to do startups and AI, you should actually have this kind of thought process and this intense practice you should be doing. Okay, that's where from the day when I say you should be intense, you should be intense. By now I was able to show some example that needs intensity. Okay, so did you understood the basic concepts of YOLO algorithm? Will not cover the whole YOLO algorithm because every 3 months you get a new version there. Okay, got it? Any questions here? No. Okay, so if you have to do landmark detection, there is a phase, right? You want to predict whether the person is happy or sad. To do that, you may have to identify the cheeks, how the shape of the cheeks are, and whether this shape of the cheeks is happy or not happy. You want to identify the eyelids and eyes and the teeth and the lips, the positions of all that, right? Based on that, you build a classification model and you pass a picture. It will be able to predict whether a person is happy or unhappy, right? Did you understand what I said just now? No? Yes? The problem statement is, I'll give you a picture. You have to predict whether the person is happy or unhappy. To do that, what all we need? That's the question I was trying to ask. Can you tell me? I'll give you a picture. You need to pass it to your model, and then that model should predict whether the person is happy or unhappy. To do that, how do you prepare the data set? right? Data set is the key thing, right? How do you prepare the data set? How do you prepare?
The first step will be convert that into numeric format
Yes, and good.
and do the multi-label, multi-labeling the output variable
Yes, yes. By variable, right? How
by
you will do?
variable.
Yeah, you actually, there are, there are two classes, right? Happy and unhappy. But internally, there may be other classes also, whether cheeks are maybe are happy, unhappy, right? Happy, unhappy are the two classes. And then you actually need to take the pixels, maybe 4 pixels here. 1, 2, 3, 4. 1, 2, 3, 4, 8 pixels here. And then maybe 1, 2, 3, 4, 1, 2, 3, 4, 8 here, 8 here, 16, right? 16 plus 8, um, 16 plus 8 is 24. And then for lips also you may have to take 8. That means 32 pixels you have to take as the output. And 32 variables, maybe the eyebrows also you have to take, right? That is called as landmark. There is a landmark detection, model in OpenCV, right? You can actually experiment with that. But the guys who actually built those models, trained those models, went through a lot of pain and suffering, right? Of manually labeling the data. Without manually labeling the data, you cannot do anything. Many people doesn't know. In the industry, many people doesn't know. Most recently, I have seen people who are actually like, it's a loot, I would say, right? Loot. When you are not doing any good to the money you take, it's a loot. Okay. So landmark detection. In previous object detection, we had a DXBY whatever landmarks, right? The target label should have these landmarks along with the object presence or not present. Whether a person is present or not, right? Object present is not, or not, or person is present or not, then the landmarks. If we would like to detect emotion, the landmarks must be many, right? Many such that eye corners, cheeks, teeth, etc. Plus classes such as smile, laughing, crying, right? So we have to create a labeled data set with these landmarks before start building the CNN model. So the basic point is data set, labeling data, appropriately labeling data, and what is the problem we are trying to solve and how the labeling should be. We should understand all this. Got it? This is the key. That's where, right, the industry is trying to pay a lot to the people who do AI. Do we have all problems like this in industry? No. This is very rare. This is very rare. Maybe 90% of the times you will not get these kinds of problems. You'll be able to solve problems with the existing models and things like that. Okay. Any questions here? Okay. So in YOLO algorithm, right, there is another concept called as other concept to handle overlapping images. In a same picture,
So
you may have
can you please go back once? Sorry.
there. That's it.
Yeah. So we are trying to, let's say, detect whether a person is smiling or whatever his emotions are. So if the size of the person is different,
Size
then
of the
how
picture.
picture,
Size
yeah.
of, uh-huh.
Picture.
Then
Maybe the
then
size of the picture is the outlier, the outline is the same, but inside the picture, if this image, the person's image is bigger,
you
it
take
occupies it occupies.
while training the model, right? You take multiple pictures, right? So maybe 10,000 pictures you take and then label it and do. In that sample, right, you will have different sized pictures, right? That way, model will work. If it is not working, right, that means the data set is not sufficient. You need to take more images of that particular set. That's where when you do a deep learning model or a machine learning model, there will be error, right? You cannot solve 100%. Got it?
Yes.
Right? You got the answer, right? The data set is the key. You need to take different, you need to understand how how your business works, what you get in production by looking at the data, and then pick the data set, pick the training data set appropriate to your production data and try to build it. That's where for every company there should be an AI team. Rather, if you can build a universal model that works for everything, right? All software engineers jobs will be gone. Only data scientists will work, and those that too maybe 1,000 or maybe 5,000 people. That's it. And, IT industry will be closed, right? Got it? Every problem is different, and pre-trained models will give you base only. You need to use transfer learning to uh, because you will not have huge volume of trained labeled data, right? And then train models and make them work on your production problems. And answered? Still question?
Yes, sir, got it.
Sir, are you using the same tool, ImageLab tool, to identify the cheek and
No.
then,
This I did not do. This is actually present in OpenCV. OpenCV landmark detection. If you say OpenCV models, you can directly copy. It's an API, but you cannot train it. You cannot train it on your data, but you can just play with it. It's a kind of playing tool, I would say.
okay, sir.
See this landmark detection. There is a landmark detection model that actually does that. See that. It detects the landmarks, but you can build a model to find out whether the person is happy or whatever. Right? You may have to do additional stuff. I think I never used it, but this is the thing. OpenCV has got tools with which we can play, and OpenCV has got some methods, right, which will actually help us in pre-processing the data. Now, converting the image into grayscale, kind of finding missed pixels, like those kinds of things. I'll explain you. There is concept called as dilation and erosion, and that is used in some of these number plate recognition models. I'll show you. I'll actually explain that later. Okay. So landmark detection I did not do because it's a very tedious task to create data sets. But the team I have and the time I have, right, I cannot do it. Okay. So Microsoft, Google kind of guys can do it because they have budget and people and all. Good. Can I move on? I'll take 10 more minutes because I wanted to give you an exercise which is worth doing. Right? It will be useful in your real time. Okay. Is it okay if I take 15 more minutes?
Yes, sir. Good.
So in YOLO algorithm, right? YOLO is one algorithm. There are RCNN, fast RCNN, faster RCNN, fast RCNN. Some models are there which will actually do the object detection, but they are slow compared to YOLO. What YOLO does is you look only once. Is the YOLO? You look only once. What is that? You look only once. This is what it is. You look only once, right? This is actually the sliding window thing, right? It is actually looking only once. This is the concept, okay, for YOLO. So in YOLO, right, it can identify multiple objects with same origin. Okay, here the person and car both have got same origin. In this case, right, you need to have two sets of target variables, right? Whether the person is present or not, and then what is the class it belongs to, car. Whether whether car is present or not, what is the class, and what are the bounding boxes of it, and whether person is present or not, what are the bounding boxes and person classes, whatever. Right? If you have YOLO algorithm by default supports 5 different classes at once. So you will have 5 sets of these. For 2 classes, you need to have 2 sets. For 5 classes, you need to have 5 sets. These 5 things will be useful only when the images are overlapping. See this here. What I said, in a particular 3-dimensional block, you will know whether elephant is present, or dog is present, or cat is present, or horse is present, or elephant is present. Only one, right? I am saying, because the origin is one, right? So if you have 2 images overlapping each other, a dog and a cat, or a horse is there, maybe at the foot, it is near its legs, right? There may be a cat sitting there, right? So they both are overlapping. Then you need to have 2 anchor boxes, we call them anchor boxes. Okay, they call it as anchor boxes. It's called as anchor box. If you see on the right side, let's call it as anchor box. We have C1, C2, C3, out of which only one is available, right? So here, there is a overlapping anchor boxes, right? You need to take like this. See, there is dimensionality and all, you will get confused. So this is what it is. And generally, what we do is there are 8, right? So for each of the object, there are 8 variables, right? If there are 3 different objects you want to find, it's going to be 3 by 3 by 16. If you want to identify 5, it's going to be 5 by 5 by 16. The target variable is going to. So don't be worried about it. That's try to look at this theory. And this next thing, right? I tried to do object detection in Windows machine, on Windows machine. It is too tedious. If you want to try, right, these things are there, but don't try it. It's going to waste like days long time. Okay. On Saturday, we look at face detection and one-shot learning. That's another exciting topic, and this is a real-time, need actually, right? So now, right, I'll actually show you a resource where you can do object detection on your own. Okay. So in TensorFlow, there is a resource called as Model Zoo. Write it down. Please write it down. Model Zoo. Okay, TensorFlow 2 Model Zoo. Right. In this Model Zoo, you will have already pre-trained models here. See this? CenterNet, Hourglass Net, these are all different networks. Right? YOLO is not there. YOLO is a third-party one. Faster RCNN, right, with ResNet, right, and MobileNet, right. All these are different networks. You can actually take these networks and retrain on your data. Okay. So I'll show you one place where you can actually find how to train it. Okay. This guide. So you go to this Model Zoo. You will have a guide here. Not this one. Sorry, not this one. TensorFlow Object Detection API. Yeah, this is the one. This is one. Very good resource, and it is very easy to do. Object detection at real time is very easy to do. Okay, just follow the instructions here and do it. Please do it. So this is one resource, and from this is where you can actually take the model you want, and you can actually take pictures. You want to do. I did a model called as onions and potatoes. Okay. Right? You take onion, pictures, then do bounding boxes. Take potatoes, right? Potato images, do bounding boxes, and maybe 1,000, maybe car and bike, car images in the traffic. These are individual images, but if you take onion, right, they're multiple, right? They're multiple, and you can take vegetables, different vegetables, and then try to pass that to model and ask it to predict. It will predict it. Onion is there, or potato is there, or tomato is there, like that. You take 100 images, use this tool, do labeling, right, and then follow this tutorial. Follow this tutorial. They actually explained everything, right? You can do this on Google Colab. Don't do it on your machine. Do it on Google Colab. Okay, there is no Colab notebook also was given somewhere here. Somewhere here. Okay, so this is XML files you create, right? Just follow these instructions. You will be able to do object detection. Got it? Got it? Yes, no? Will you do?
Yes, sir. Which data set we need to take, sir?
We need to prepare that. We need to collect that also. Let me see if there is some data. We need to collect the data. Yeah, this guy actually did it, but this data set is not useful for us. We have to take the data and then you need to actually label it. This is the one I actually experimented on, and I'll put this on. There will be some data somewhere, but label data is not going to be there. You have to do it, I think, like this. You follow this article. First follow this article, these articles, and then try to follow this, or take data from the Google and label it on your own and do it. That will give you a clear picture on what you need to do in object detection. Don't follow the third article, follow the first two. Got it?
So when you say take data from Google, you mean take images of whatever the vegetables, multiple images from the Google.
Take onions and pickles, onions and pickles, or onions and tomatoes, kind of a thing. Right? 100 images here, 100 images there. You can work as a team. Actually, you can collect data and then start labeling, discuss together, right? Create. So if you look at this article completely, you will know what to do. Right? This tutorial, right? This tutorial completely, you will know what to do on the data set. Right? Do that as a team. If you have 100 images also as a team, right? You can do it in 15 minutes. We are like around 6 people right here, right? Each one takes 50 images also. You will be able to do it in 15 minutes, and then you can do that model. Maybe you want to do this, you take the data set from here and then do the labeling there. Got it? Only look at this article for the data set only. Okay? Rest is all present here in this. Official documentation this is. Got it? Yes, no? So jump in and see. It is easy only. It's very easy.